Hello, Honors Chemistry, and welcome to titration. So, this is section 14.6, super duper important section. This is going to be what our lab is based on, the chemistry we talk about here, so make sure that you are good on this. All right, so titration can be used as an analytical chemistry technique used for all sorts of different reasons and in all sorts of different ways, right? The key thing, right, is that no matter what way we do it, right, so it's introduced in this chapter because we are going to talk specifically about acid-base titrations, right? But again, titration can be used for all different kinds of reactions as long as we have some way to mark the equivalence point, right? But for our purposes, right, and for what you need to know, right, titration as an analytical technique, right, allows us to determine moles, right, of our unknown, right? It always allows us to determine the moles of our own unknown, or we can always look at it as the thing in the flask, okay? So what that means is that every titration is composed of multiple parts. We have this part in the burette, that's always going to be our known, right? So for that, we need to know the concentration. So it has a known molarity, right? And because it's graduated, we are going to know known volume added, okay? Known volume added. So if I know the molarity and I know the volume added, that means by extension I also know, right, that means I know the total number of moles added, right? I know the number of moles added, again, like it goes in your book, right, to reach the equivalence point. We're at the equivalence point, right, the moles of known added are equal to moles of unknown originally present. And that part's really important, right? If you try to shortcut the phrasing, if you try to shortcut the wording there, odds are you're going to miss the point, right? Because you're going to try to turn it into something that it's not. It's always going to be the moles of known added equal to the moles of unknown originally present, okay? So then going back to our figure, here in the flask is our unknown. So what it means is it's usually an unknown concentration, okay? We can use it for other things, right? Because again, the whole goal is to determine moles of whatever it is, but usually it's an unknown concentration for this purpose, right? With a known volume, okay? Now, if I know the moles of stuff added, to reach this, which is the equivalence point, when our indicator changes color, right? So an indicator is some chemical that we can add to the reaction that will change color when we reach the equivalence point, where the equivalence point means the moles of known added equals the moles of known originally present, okay? So at that point, the moles added equal the moles of my original, whatever was originally present. So if I take that number of moles and I divide it by my volume, right, that's going to give me the concentration of my unknown. Yes? Does that make sense? All right, looking at it a different way, right, a couple of things to think about in terms of species, right? So up here, we're going to have our base, right? So in this case, this would be a sample of aqueous NaOH, where the key component is actually the hydroxide, right? So that's a hydroxide ion, right? Down here, we have our unknown acid, unknown concentration, okay? And so those little gray dots just symbolize the H+, because that's the only part that actually matters, right? So what that means is we are going to add, if we look here, we have 1, 2, 3, 4, 5 acids, right? So we could say 5 moles of acid, 5 molecules of acid, 5 ions, whatever you want to talk about. But the point is that that means if we watch our titration, right, as we go from here to here to here, right, we start off with 1, 2, 3, 4, 5, 6, 7, 8 moles of hydroxide, for example, and after we've added, and here we have 3 left, right, so we started off with 8, here we have 3 left, 3 remain, right, which means we added 5, yes? That makes sense? So if I added 5, right, that tells me that inside my flask I must have had 5, yes? Does that make sense? If I added 5 moles, that means my flask must have contained 5 moles, yes? And when we reach the equivalence point, like this picture shows, right, there is no reactant remaining, yes? right? So at the equivalence point, there is no reactant remaining. What should have happened is we should have exactly reacted all my reactant, and there should only be product left, okay? All right, so let's go ahead and do a practice problem to see what this actually means in terms of math. So it says that we have 10 milliliters of a monoprotic acid solution. So this is my volume of acid solution, and monoprotic means that there's only one H+, okay? Are titrated against 0.2 molar NaOH. And I would like to know the original concentration of my monoprotic acid if this much NaOH is required to reach the equivalence point. So again, equivalence point is where my moles added are equal to the moles originally present, okay? So if I think about this, first let's write a reaction, right? So I have NaOH, aqueous, plus my monoprotic acid, so I can symbolize that as just being HA, aqueous, right? Where A doesn't matter what A is because the A is insignificant to this process, right? And I know that I'm going to make some water, and I know that I'm going to form a salt with what's left. And since that salt is stuck to a sodium, which is always soluble, I know that that's also going to be aqueous, right? Which then allows us to get our mole ratios, right? Because we can't do this because it's a chemical reaction without mole ratios. So now I'm going to start with my 15.22 mils of NaOH. And then I am going to convert that to liters. And then I'm going to get to moles, right? Because again, that's our key here. So 0.2 moles of NaOH for every 1 liter of NaOH. So at this point, right, up through here, what we have calculated is this is the number of moles of NaOH added. Okay? Now what I'm going to do is I'm going to relate those to the number of moles of acid, right? Based on my reaction, I know that for every 1 mole of NaOH, there was 1 mole of my acid present, yes, right? And so then we put in the mole ratio, and this is going to tell us how many moles of acid were present, yes? This gives me 0.00304 moles of HA. So this is how many moles were originally present. Yes, does that make sense? Number of moles added equals the number of moles originally present, okay? Now, going back to the question isn't asking for moles, it's asking for the concentration, which is what unit? Molarity. So I'm going to take my moles of acid, and now if I need to turn that into molarity, I'm going to go back and divide it by the volume from which they came, yes? If I want the original concentration, I'm going to divide them by the number of milliliters from which they came. I think I said moles, but you know I mean milliliters, right? That is the actual answer. Yes? Does that make sense? All right, go back through this math, make sure it makes sense. Really, really important stuff. Where the actual math is not hard, it's just making sure you understand the information being presented and what to do with it. All right, thank you for listening. Be good, and I will see you soon. Bye.